Morning. We'll get started now. I guess we're at 10:10. So thank you all for being here. We are going to talk about something that's technically not on the exam today, but I think it's helpful because we'll start to see how doing all of these cycle analysis problems can be kind of collapsed into one thing. So you won't be doing this specific Rankine reheat problem that we're going to do on the exam. But if you can understand sort of the general method that we're going to use here, I think it'll be really helpful for, moving into how you're going to do the 4-component Rankine cycle on the exam. So just a reminder, the exam is this Thursday. I am assuming that everyone will be writing at the same times as they did in the previous exam. And we'll have basically the same layout, that there'll be 10 multiple choice questions and 2 long answer problems. And those things will be sort of separately made available to you for these different parts of the exam. So just if you have a conflict with your times, if you're not available at the times listed or on the same day at the time that you wrote the exam last time, please let me know if you have a conflict. And just like last time, we'll have the same kind of late penalties that were associated with materials not submitted on time. We're going to do an example today on Rankine reheat. So just a reminder, as you start studying for this exam, or when you go back and studying for the finals, you can always find the sort of starter sheets or PDF versions of these problems that we're going to do. You can see them all just on the My Courses website under the lecture series part here. There's Schertzer's pre-recorded lectures and starter sheets. So in here, you'll get links to the YouTube videos for the complete captioned versions of all of our lectures. And then you'll also get links to PDFs for the problems that we do in class. So, I mean, obviously, I'm not unbiased here, but I do think that, we've been trying to learn that thermodynamics is actually really important, right? So it's this thing that we use, this understanding of the universe that engineers and scientists have been using for a long time to try to improve the quality of life for people in everyday society, right? In particular, right, we're using what we know about thermodynamics now to learn kind of how we keep the lights on, right? How we power these computers that we're using to, to either give or receive the lecture today. And we do that by using heat engines, right? So like I said before, for the Rankine cycles that we're talking about, almost half, a little bit less than half of the power generated in the US, at least in 2019, was generated using Rankine cycles, typically coal-fired and nuclear-fired power plants. And when we're trying to ask ourselves kind of how good are we doing, when we're trying to characterize how well these cycles, these heat engines are doing, we talk about thermal efficiency, right? So this is definitely something that will be on the test, thermal efficiency, even though we won't talk about it with the cycle that we're talking about today. So this thermal efficiency is always going to be all of these characterization parameters, whether it's thermal efficiency or coefficient of performance, they're always going to be the energy benefit of the cycle divided by the energy cost. Now, when we're talking about heat engines, the benefit is the net power that's developed by the engine, and the cost is the heat that we have to put in. And then we know that this is always going to be true, right? And then if it's an ideal or Carnot engine, then we can make some substitutions and get this into a formulation to find the maximum efficiency using the temperatures. But we do have to be careful here because the temperatures we have to use are absolute temperatures, right? Particularly here in the denominator, or if you rearrange this to be 1 minus T cold over T hot, because then it wouldn't be temperature differences, you need to use Kelvin or Rankine. Right, so that's when people ask, what's a common mistake people make on exams? Not converting to absolute temperatures in equations that have temperatures that stand alone, right? That don't have temperature differences is a super common way that people make mistakes on these exams. right? As we said, Rankine cycles, which is what we're still talking about. So we'll be talking now about an evolution of a Rankine cycle to try to improve efficiency, but they make up just about half, a little bit less than half of the power that we generate here in the United States. We did an example before for our 4-component Rankine cycle, right? This was, I believe we had turbine and pump efficiencies of 85% in this cycle, and we found that the thermal efficiency was 28.4%. And I think the maximum efficiency of this cycle, when we looked at it, was somewhere in the 50s, maybe like 55% or something. I don't remember exactly off the top of my head, but certainly there's room for improvement, right, from this 4-component cycle. So then we started to talk about improving efficiency, right? And we said, well, there's 2 main arguments for why you want to improve efficiency, right? The first is a financial argument that if your power plant runs more efficiently, it either means you're burning less coal or you're producing more power for every ton of coal that you're burning, right? And both of those things are good from an economic perspective, but it's also good from an environmental perspective because it means that we can produce the same amount of power and have less emissions, right? Particularly if we work on, different ways of maybe recapturing those emissions so that they don't get out to the environment at large, right? So there's this environmental and economic argument for improving efficiency, right? So how do we do this? We talked about, we can increase T-hot, we can reduce T-cold, and we'll definitely do both of those things, right, in real life. But then we said, well, one of the things we can do is we can learn how to be master builders, right? So we can increase the complexity of these cycles, right? And the first way we talked about doing that is by doing a reheat cycle in this Rankine cycle that we know, right? So on the exam, you won't have to deal with reheat, but in the example that I'm going to do, it's all the same process. So I think it's still useful for the preparation for the exam on Thursday, right? Now the difference between the 4-component Rankine cycle and the reheat cycle is that we have this second turbine, right? So now we have a high pressure and a low pressure turbine, and in between them, we go back into the boiler or steam generator to reheat the fluid before it goes into the second turbine. It's kind of like, we've already got the oven there. Why don't we reheat this fluid so that we can put more enthalpy into the fluid so that we can get more work out of that second turbine than we otherwise would have. But the process here is still the same, right? So if we want the thermal efficiency, which is what we're going to try to find today, we still take the net power divided by all the heat that goes in. We still then use the first law to get some equations. We'll still then ask what's the fluid to try to fix the states. And then once we fix the states, we'll get numbers and we'll put them in, right? So it's a little more complicated because there's more terms, but the process is the same, right? So that's the thing. I think the thing about thermal, one of the reasons that some people I think strongly dislike thermal is that if you're kind of a memorizer, if that's how you learn things, right? Or how you have learned things in the past, there's just like so many different wrinkles, right? And personally, I think, at least for me, it's not a good strategy to try to memorize all the possible different wrinkles of how you can do a cycle, right? It's better to understand, to sort of have this deep understanding of the process. Because if you understand the process, it doesn't matter what the wrinkles are, because you follow the same process every time, right? And that's kind of the way that I'm trying to teach this to you, right? So if we're trying to find thermal efficiency for this cycle, it's the same as thermal efficiency for any cycle, for any heat engine, right? We have the net power divided by the heat in. But now we have 2 turbines that are producing power, right? So there's 2 positive power terms. There's still 1 pump, so there's only 1 negative power term. But now there's 2 places to add heat. Now, personally, for me, and this is kind of stupid because it's called a reheat cycle, but for me, if I'm going to forget something, it's usually this second heat addition term, right? So remember that it's called reheat, right? There's 2 turbines, yep. But there's also 2 places where we're adding heat. I think it's because when I draw it out, I usually don't draw this as a separate device, right? We go back into that other device. So I think that lets me sometimes forget that there's that heat addition, right? But we're still going to go through, and now, so now we got this equation for thermal efficiency, and we say, oh man, this is great, except I don't know the power of the first turbine, the power produced by the second turbine, the power consumed by the pumps, or the heat addition in either place, right? So now I got to look at those terms and say, well, how do I get equations for those different terms, right? And the answer, as is often the case in thermodynamics, is use the first law, right? So if you feel like you get lost here in the second exam, write down the first law, right? Try to make some assumptions about whatever's going on, and then you'll get some kind of an equation, right? And hopefully that's an equation that's helpful for you to solve the problem, right? So here, I just write down the first law once, but I always write down the whole version of the first law, right? And then I keep track. I like to use different colors, right? But you can do it however you like. But I like to use different colors to remind me which assumptions I've made for which component. Right? And typically, but not always, if I'm talking about a power generating component, like a pump or a turbine, then it's steady state, often one inlet, one outlet. Usually we neglect kinetic and potential energy, and we say that it's adiabatic. But if it's a place where I'm adding heat, then usually I'll say, oh, it's steady state. It's usually one inlet, one outlet. We usually neglect kinetic and potential energy. We're going to neglect any kind of friction losses inside that device. So it's the same pressure coming in and going out. And then we'll get an expression for the heat transfer rate, right? And then in between the lines that connect all of these different components, we'll also say, well, we're not going to consider friction losses or heat losses in those things because otherwise there's just too much work to do. Right, too many states to fix, and it's they're minimal compared to say the power that's being generated by the turbines. So we're going to neglect those things. And if I can make all of these assumptions, which I may or may not be able to do on an exam, then I'm going to get expressions that look like this, where if I'm trying to find turbines or pump powers, it's going to be the mass flow rate times H in minus H out. Right, but I recognize that if I'm using the first law, that means that I'm embracing this hip to win sign convention so that the turbine power, the power produced by a turbine, has to be positive, right? But the power consumed by a pump has to be negative, right? So I add those things up and my net power is less than my total turbine power. If I'm trying to find a heat transfer rate, then I'll get that the mass flow rate, I get that Q dot is equal to the mass flow rate times H out minus H in. Right? And again, I can fix the states, and I expect that the boilers where I'm adding heat, that's going to be a positive number, and the condenser where I'm rejecting heat, that's going to be a negative number. Right? So then I get to this point, and then I say, what's the fluid? Right? And because we're still talking about Rankine cycles, it's some kind of fluid that's going to bounce back and forth across the vapor dome. Right? So that means that we're going to ask ourselves not just what's the fluid, the answer is probably water in this case. Then we got to ask ourselves, well, what's the phase? Right? Is it liquid going into a pump or coming out of a pump maybe? Is it a superheated vapor maybe going into a turbine? Or is it a two-phase mixture maybe coming out of a turbine? Right? And when I get that, then there's different strategies for how I go through and fix those states. So now I'll pause to see if there's any questions, and then we'll go and we'll do this Rankine reheat example. So does anybody have any questions about this reheat Rankine cycle? Okay, so I will close this. So this is going to be our problem. So we have this Rankine reheat cycle, right? And I'm gonna, here, let's just erase this, right? Maybe the first thing I'll do is draw the TS diagram, because that's certainly something that you could be asked on an exam, even if it would only be for a 4-component Rankine cycle, right? We have this state table. This is maybe the kind of state table you'd see on an exam where, yeah, there's a lot of states, right? But most of them are kind of filled in already, right? So some of this stuff is filled in already because we did it already, because here we're taking the same states as we can that we did from the previous example, right? So here, this is the same state going into the first turbine. It's the same state coming out of the condenser, going into the first pump, coming out of the pump and into the boiler, right? So a lot of this is the same because we're going to compare the efficiency we get here to the efficiency that we get in that previous 4-component cycle that has these same isentropic efficiencies for turbines and pumps. So here it says, what's the thermal efficiency? But I'm also going to say, let's draw the TS diagram too. Right? Although, again, down here, we'll pretend this isn't here, I guess, right? So here, for the TS diagram, how do we do this, right? So let's think about how we do this, TS. So the first thing that I ask myself is, what's the fluid? And because it's water, that means I need a vapor dome, right? So any kind of cycle where the fluid is water, it means that you have a vapor dome. Right? Now the next thing that I do is I look to see how many pressures are in the cycle. So this is the highest pressure, right? But then as we go through the first turbine, the pressure goes down. So then there's some intermediate pressure. And then we go through the second turbine, and then there's some kind of low pressure here. And it stays at this low pressure until we get to the pump, and we're high pressure again. Right? So here I got to draw 3 constant pressure lines. So this is going to be my low pressure line. Here, this one is my intermediate pressure. And this one is my high pressure. I guess I'm assuming that all of these things go through the vapor dome. Right? So that, none of it is supercritical. Right? Because we did talk about how one of the things you can do to improve efficiency is you can push this high pressure up so that it doesn't come through the vapor dome anymore. So now I'm going to assume, and I guess I could look at the state, right? And I could say, see what's actually going on. But here I'm going to assume that going into state 1 is a superheated vapor. Now, I have isentropic efficiencies in this case, right? So then I'm going to draw this kind of imaginary line, this vertical line down from state 1 down to state 2s. So this gray line, that process doesn't really happen, right? But we can pretend it happens, right? And then I'm probably exaggerating this to get to the real state 2. So now this goes down and to the right. Now here, right, from state 2, now what do? We go into, so that was from state 1 to state 2 is through this turbine. Then we heat up a little bit. And as we heat up, that means we get pushed to the right on some constant pressure line. So what's happening is as we add heat, because we can't evaporate any fluid because we're already superheated vapor, we're going to follow this constant pressure line up to state 3. Right? Now, we're going to go through an imaginary ideal turbine from state 3 to state 4s. And then we'll go through the real turbine to state 4. We'll pretend this is on the same pressure line. Right? Now, you can see here versus the actual example that the textbook drew, right? Mine is in a different spot, right? So it could be, I don't know if state 2s or state 2 is under the vapor dome, or if state 4s or 4 is under the vapor dome or here in the superheated liquid region. So when I ask you to draw these things on an exam, it's okay if these things don't land in the exact same spot. When we do the analysis, we're going to have to ask ourselves what's going on with state 2s or state 2, right? But now, so now we got state 1, we got state 2 and 3, right? Now we got state 4. The next thing that happens is we go through the condenser. So here we've assumed that there's no pressure losses, right? So we stay on this low pressure line and we cool the system down, right? And we cool it down all the way to some saturated liquid. So now this is state 5, right? Because this is a heat transfer process. We don't need any kind of like 5S or anything, right? Now we're going to go through a pump, right? So from 5 to 6, first we would go to, and 6 takes us all the way back up to the high pressure, right? Not the intermediate pressure. So here we go up vertically to 6S, right? Again, the distance between these lines is kind of exaggerated here so we can see it, right? And then the real process is going to take us from state 5 to state 6, going up and to the right. And then we go through the boiler at constant pressure to add heat. Right now, the other thing that I like to do, which you don't have to do on an exam, but it helps me, right? So this is going to be Q in, right? There's another spot here where we're adding, this is also going to be Q in or Q dot in, right? This is going to be Q dot out at the condenser. There's going to be power produced by the first turbine, power produced by the second turbine, and power consumed by the pump. I like to draw these things on because already I can see, because I know my thermal efficiency equation is going to be W dot net over Q dot in. So because I've drawn these things, right, I can see that this term is going to be important. This term is going to be important where I'm adding heat. I'm producing power here. I'm adding heat there. All those terms I'm going to need. This one, though, I'm not going to need for this expression. So I kind of like to draw these things out so I know which processes I'm going to end up needing for my thermal efficiency. So this is my general process on how do I draw a TS diagram, right? So I figure out how many pressures there are. Well, first I ask what's the fluid, because I need to know should there be a vapor dome, or if it was just an open system problem that you might see on an exam. If it's ideal gas, then you don't draw a vapor dome on a TS or a PV diagram. Right? Then I say, okay, how many pressures are there in the problem? And then I kind of go component to component, sketching out what happens in the component. So turbines, we're going down and to the right, down and to the right, right? Or if it's ideal turbines, they go straight down. Pumps, we're going up and to the right if they're real, or just straight up if they're ideal. And then if it's a heat transfer process, we're staying on the same constant pressure line, but if we're adding heat, then we're moving right to left. No, left to right, sorry. And if we're rejecting heat, then we're moving left or right to left, right? So then we're going leftward. Right? So that's kind of how I draw these different TS diagrams. Right, and that's, again, I'm trying to be sort of like a general process for how do we do these things. Okay, so now what the problem actually asked us, right? So here I just did this to kind of show you because you might have to do that on the exam, draw a TS diagram. So now the problem asks, what's the thermal efficiency? So for the thermal efficiency, we know that this is going to be W dot net divided by Q dot in, right? And we already found that there are 3 places where we have work or power involved and 2 places where we're adding heat, right? So I can more generally call this, and I like to color code things, right? So, oops. We're going to say here, I think the reason that happens is because my cursor is not in the right place. So let's try if I leave my cursor there. Hopefully we'll avoid more of that. Right, so here we're going to take the turbine powers, the sum of all the turbine powers, plus, the turbine powers are positive, plus the sum of all the pump powers. And because the pump powers are negative, they're going to lower our net power. And then we're going to add all the places where we add heat. Right? So now, right, if I want to do this, I can more generally say, okay, I've only got one pump, right? So that's good. I only need one of these, right? That's this one, right? I got two turbines here and here, and I got two places where I'm adding heat, right? So here, this is going to be, again, I'll stay with this color coding, W dot of T1 plus W dot of T2 plus W dot of the pump divided by Q dot of the boiler plus Q dot for the reheat process. If you prefer, instead of subscripts that are letters here talking about the components, you could put the subscripts here too, right? So this could be W dot 1 to 2, right? And W dot 3 to 4, and W dot 5 to 6, and Q dot 6 to 1, and Q dot 2 to 3, right? So that's also acceptable. So this is great because I've got my first kind of symbolic equation here. The problem, of course, is that I don't know the thermal efficiency, I don't know the turbine power, I don't know the pump power, and I don't know any of the heat transfer, right? So I got an equation, but I don't know anything about it, right? So now what do? I think about, okay, I've got to find these expressions that will tell me what the turbine power, the pump power, and the heat transfer rates are, right? Hopefully, at this point, we realize that means it's the first law, right? But if not, if you really feel lost, guessing that you should do a first law analysis is never really a bad idea, right? So here, we are going to do a first law analysis. And again, I'm always going to encourage you to write down the whole equation. So it's dE by dt is equal to Q dot minus W dot plus the sum of M dot in H in plus V in squared over, it's only 2 and not 2GC because this is a metric problem, plus GZ in minus the sum of M dot out, H out, plus V out squared over 2 plus GZ out. So now, because I recognize it takes time to write this equation down, and maybe it's a test situation, so I don't want to write out this thing like 5 times. So I'm only going to write the equation once, right? And now I'm going to look. So for all of the components, I'm going to say that they're all going to be steady state. So they're all steady state. I'm going to neglect kinetic and potential energy changes for all of the components. And here I can look back here and I see that for the parts that I'm interested in, the pump has only one inlet, one outlet. This boiler, right? The first stage of the boiler, one inlet, one outlet. The turbine, one inlet, one outlet. This part here, all of these things have one inlet, one outlet because I don't have, sometimes for the condenser, although the condenser I actually don't care about here, right? Sometimes the condenser can have some cooling water that's coming in and out. So it's not one inlet, one outlet, right? So all, I guess here, this is T1, T2, pump, boiler, and reheat. So we're not talking about the condenser. So they're also all one inlet and one outlet. Now, for the turbines and the pumps, I'm going to say that they're adiabatic. So Q dot is equal to 0, but only for the turbines and the pumps. And then for the heat transfer, right? Well, I guess instead of calling them heat transfer terms, right? How about I call them for the boiler and the reheat? I'm going to say that they're passive. So when I do that, what do I get? So when I do this, I'm going to find that if I'm trying to find W dot, it's going to be M dot times H in minus H out. And if I try to find Q dot, it's going to be M dot times H out minus H in. Oh, and I guess I've skipped a step, right? And sometimes this is, you know, on an exam, it's good to demonstrate your understanding, right? So here, because the other thing I can do, right, for all of these components, I could do conservation of mass. dm by dt is equal to the sum of m dot in minus the sum of m dot out. But if I look at the assumptions that I've made for all of my states, right, they're all steady state, they're all one inlet, and they're all one outlet. So these are all m dot in is equal to m dot out. So there's only really one m dot in my problem, right? So the same mass flow rate that goes through the pump, right? It comes into the pump, goes out of the pump, but that mass flow rate that comes out of the pump goes into the boiler, right? Et cetera, et cetera. Because these are all one inlet, one outlet, and they're all chained together in series. So there's only one mass flow rate in the problem. Here, I'm going to bring this picture down because it's nice to have the picture. Okay, so what do we do now, right? So here, I know that my thermal efficiency equation, right, was equal to my power of turbine 1 plus power of turbine 2 plus the power of the pump plus Q dot in at the boiler plus Q dot in at the reheat, right? So now my first turbine, right, T1 is up here. It's going to be m dot times H in minus H out. So this is going to be m dot times H in is state 1. So this is H1 minus H2. Right? My second term here for the second turbine is going to be m dot. The inlet to the second turbine is state 3, H3 minus H4. Plus, now my pump is going to be m dot times H5 minus H6. Now, I didn't do these color-coded, but I'll do this now. I expect those two terms from the turbines to be positive and this term from the pump to be negative. So my total net power will be less than my turbine powers, right? That's why this has to be plus that negative number. I got to remember, like I said, if I'm going to forget something, it's probably the reheat in this equation. So here I have two terms that are going to be m dot times H out minus H in. So this is going to be m dot times H out, right? So H out here is H1 minus H in is H6 plus the mass flow rate here for the reheat is m dot times H out is state 3 minus H in is state 2. Now, because all these mass flow rates are the same, I can factor mass flow rate out of the numerator and the denominator. So the fact that I don't know the denominator is okay. Right? So now I can say that this thermal efficiency is going to be, I like to keep the brackets, but you don't need it. H1 minus H2 plus H3 minus H4 plus H5 minus H6 divided by, oh, wow. I was going to say we're going to pretend that line's straight, but that was just, it's a little, I can't do it on this path. Although that kind of implies that I can draw straight lines on the board. You haven't seen me try, but I'll let you know that it's not great. It's a little bit like a constant specific heat assumption, where the longer my line is, the less straight it becomes, right? So just like constant specific heat, the further away the bigger your temperature difference is, then the worse the assumption gets. So a question from the chat. So for thermal efficiency, you're adding all the W's over all the Q ins. Yes, that is true. The textbook will tell you, right? So I add all these together because this is, again, positive plus a negative. So because I get the equation from the first law, and my power is always going to be m dot in minus, or h in minus h out, then I add them all together. The textbook tells you to add the pump power, or to add the turbine powers and subtract the pump powers, but they're going to tell you that the pump power is m dot times h out minus h in. And they do that, it's the absolute value of the pump power, but you can't get that expression from the first law. So I don't like to do it the way the textbook does it, because again, I'm trying to minimize as few things as I can. I'm trying to collapse all this stuff together so that I don't have to memorize all that stuff, right? So I add them all up, even though some of them are going to be negative numbers, right? So again, you want to check that your net power is less than your net turbine power, right? Because the pump power should be negative. So here, you'll have to trust me. I have the sheet in front of me, but we're told, right? The thing we're trying to find here is the thermal efficiency, right? Now, what do we know, right? Because now we've got an expression. We've got a symbolic solution. That's good, right? So we know H1 was given to us, or at least we figured it out before. We know H3. We know, oops, that's the wrong sheet. So here we know H1, we know H3, we know H5, we know H6, we know H1 here, we know H3, but we don't know H2. Why is this over here? I got a feeling I did this wrong. No, this is H2 because that's the inlet, right? It's H out minus H in. So we don't know H2. And we don't know H4, and we don't know H6. But if I did know those things, then I would have an answer, right? So now we're going to go through and we're going to look at how do I find all of these states. I probably won't get a numerical answer for these states. I'm just going to go through and show you how to do them because I want to get through all of them. So what do we need? We need states, the even ones, right? 2, 4, and 6. So we'll start. If you want to see the numerical solutions here, you can go to the, I think the Thermo Short has the numbers, but also the sort of full version of the lecture that's online from the lecture series. I think goes through the PowerPoint notes. You can also just check my notes, which are on my courses, right? So we want state 2. Right, this one we don't know. State 4 we don't know. And state 6 we don't know. So let's start with state 2. So this is the real outlet for the turbine. Right, anytime you're trying to find the real outlet of something, it's probably a good idea to remember that there's also an ideal outlet, right? So when I'm trying to find real states, if I don't have information, the only thing we know about state 2 is the pressure being 10 bar. So I'm going to think about my turbine efficiency, right? Turbine efficiency, you don't have to memorize this because it's on the equation sheet, but the ideal turbine produces more power than the real turbine. So the real turbine goes on top. We've already done the first law analysis of the turbine, so we know the turbine power is m dot times h in minus h out. So this would be h1 minus h2. The ideal turbine is m dot times h1 minus h2s. Right? The mass flow rates, it only makes sense to talk about real and ideal turbines if the mass flow rate is the same and the pressure difference is the same, right? So the good news here is we know the turbine efficiency. I think it's 85%. We know the inlet enthalpies, but we don't know H2S, and we don't know H2. We're going to use this expression, though, to find H2. So let's kind of isolate H2 here. So this is going to be, if I continued on to isolate this, I could say H1 minus H2 is equal to the thermal or the turbine efficiency times H1 minus H2S, or that H2 is equal to H1 minus the turbine efficiency times H1 minus H2S. Good news here is that we have an expression for the thing we're trying to find, right? The bad news is we've got one equation but two unknowns. So in order to find H2, we need to find H2S. So what's the thing we know about H2S? This is the ideal turbine, right? So this is the ideal turbine exit. I'm going to write down the second law analysis because it's the kind of thing that you might have to do on Thursday in an exam, is do a second law analysis, right? So here we'd have ds by dt is equal to q dot over t plus of the surroundings plus the sum of m dot in s in minus the sum of m dot out s out plus sigma dot. But we already know for the turbine, it's steady state, it's adiabatic, it's one inlet and one outlet, and this is the ideal turbine, so sigma dot goes to 0. What this means is that 0 is equal to m dot, there's only one mass flow rate, times s in minus s out. There's two ways this can be true. If the mass flow rate is 0, well then you get 0, but that's not very interesting. That means your power plant's not running, right? So if there's mass flowing through your system, it means that S in is equal to S out, or that S2S is equal to S1. So if I'm trying to fix this state, I have to look at S2S, right? Maybe I won't draw a box around this, right? So once I have S2S, what do? Right? So if you remember from our TS diagram, the question with S, this is really S2S in this diagram, is this going to be a superheated vapor, or is it going to be somewhere over here under the two-phase envelope, right? So is it in the vapor dome, right? So this is it two-phase sorry about that. Is it two-phase or superheated vapor? How do I do that? So I got to look at P2S, right? That's my intermediate pressure. In this case, this is my intermediate pressure, which in this case is 10 bar. So I go to table, what is it, A3, and I find what SF and SG are at 10 bar. And now I ask the question, is S2S greater than SG, right? So does S2S come over here, or is it in between these two numbers? If you get S2S coming out of a turbine as below SF, it probably means you did something wrong. It would be pretty weird to have a liquid coming out of a turbine in a Rankine cycle. So it's one of these two things. And then here, if it's over here, then you're going to go to table A4 and interpolate. Right? But if it's in here, then you're going to find X of 2S using the quality equation, and then you're going to use that to find H2S. So basically, once I figure out if this is two-phase or it's superheated, then so basically I get S2S, and from that I can find H2S. And once I have H2S, now my here I'm going to put this to a star, right? So now I'm going to put H2S into here, And that means that I can find H, right? Because once I know H2S, then there's only one unknown in this equation, and that's the thing that I'm trying to find. I'm going to, so we find state 4 in exactly the same way. So I'm not going to go through the process of how to find state 4, right? In this problem, if the problem looked like this, we would just use two different interpolation methods, that H2S here, and it would have been a superheated vapor, and H4S here is a two-phase mixture. But I'm going to go over to this ideal pump, because this is a thing that people often, it's another one of those things that people often make mistakes on in an exam. So here, if I want to find state, now this is state 6, which is the real pump. Again, because this is real, I'm going to use the pump efficiency, which is going to be the power of the ideal pump is less than the power of the real pump. So this is going to be m dot H5 minus H6S divided by m dot times H5 minus H6. Mass flow rates are the same, right? So then I can rewrite this. I want to get an expression for H6. So now here I can say H5 minus H6 is equal to H5 minus H6S divided by my pump efficiency. Or I can isolate for H6 as being H5 minus H6S divided by my pump efficiency. In this case, right, I'm trying to find H6. I know H5. I know the pump efficiency, but I don't know H6. So here is the part that people will often make mistakes for, right? So here we're going to say that H6S. We don't know that, right? So this is the ideal pump exit. So here I remember that for ideal pumps, I have this special equation for delta H. So delta H across an ideal pump is equal to V, the specific volume, at either the inlet or the outlet, but typically we'll know what's going on at the inlet. I'll make this a lowercase I to be consistent with my other nomenclature. Multiplied by, here, instead of delta H, right? So this is going to be, right? We're trying to find this in minus out. So here I'm going to say H in minus H out S. So this is going to be P in minus P out. So I'm going to put this back into this equation over here. All right, so now if I'm trying to find H6, it's going to be equal to H5 minus this new part, the specific volume, which is at state 5, times P5 minus P6 divided by my thermal efficiency of the pump. Check your units here, right? This is a metric problem. So I want this to be, because meters, or the specific volume is going to be in meters cubed per kilogram, right? But this pressure difference, I want to be in kilopascals, right? Because kilopascals is the same as kilonewtons per meter squared, right? And this is going to be kilonewton meters per kilogram, which is kilojoules per kilogram. So if this is in metric, like this problem is, then here I want it like this. Put my pressure in kilopascals, even though the problem gives it to me in bar. So I have to know that 1 bar is 100 kilopascals, because this H5, which I'm going to look up in the table, is in kilojoules per kilogram, right? So here, right, this means I would put all this in, and then I would get H6, right? So here, I know we didn't exactly explicitly go through how to get state 4, but we learned how to get state 2. State 4, we would do in the same way as we did state 2, right? And then we know state 2, and we know state 6. You can go through, like I said, either the thermal shorts or the long version of the lecture in the thermodynamic lecture series. And you can find that here, our thermal efficiency for the reheat cycle was 29.2%, right? For the 4 component, right, this was 28.4%, right? So you might kind of scoff at this a little bit and say like, oh, we did all this work and we only increased the efficiency by 0.8%. But the thing is, it's not all that much work. And if you could go into a power plant and improve the efficiency by like 1%, that's a phenomenal savings. It's a big deal. Even though I think sometimes if you get 1% different on a test, then that's different, right? But if you could improve efficiency of a power plant by 1% or of an airplane by 1%, because these things, we run them so much, it makes a big difference both financially and environmentally if we can make even small improvements in thermal efficiency, right? And we got to remember that in a real power plant, we're not just doing this once, and this is not the only thing we're doing. So we're going to stack these different complexities to improve efficiency in a real power plant. Now, you probably won't get a question like that looks like a real power plant because it's probably too complicated to do in half an hour. But that's kind of the way that we'll move forward. I'm done for today. I guess before I leave, I would like to get your opinion on whether you would prefer to have the exam review where you come in and bring questions tomorrow or on Thursday.
Something new on Thursday?
Pardon me?
Would we learn something new?
Yes, you would learn something new on Thursday. So so one of these 2 lectures will be something new, still Rankine cycles, but we'll move on to the next thing that improves complexity.
I say, I think we should do it on Thursday or before the exam. So I guess
the
Thursday.
Exam day is Thursday. So it's a question of, do you want more time to prepare the questions you might have, or do you want to ask the questions that you have and have a little bit more time to sit on them?
I don't know. What does Michael has?
Do you have an opinion, Michael? I think attendance might be higher if we do it on Thursday, because I think we have a student who's on vacation until Thursday. So
Okay.
I'm inclined to wait till Thursday if there's no objection.
I mean, I'd be okay with that since it's on the test day, and I would remember exactly what you would say if somebody had a specific question.
Yeah, and then you're not trying to learn something new on the same day that you're doing the test. That could
Right.
get confusing. Okay, your mic isn't working. Okay, Michael, did you have a preference? Is Thursday okay with you? Okay, so let's do Thursday then. So I will have a prepared lecture that's kind of the next in the series tomorrow, which is Wednesday, and then Thursday I'll just have an open lecture where you can come in and ask questions.
Okay, that sounds good. Thank you, Professor.
Thanks, everyone. Have a good day.